Okay, so let us continue with the review of premixed and diffusion flames. The next topic will be laminar diffusion flames. So, we have seen the characteristics of the premixed flames, where you have a mixture of fuel and oxidizer, which is premixed, and when it is ignited, how the flame propagates through the reactant mixture. So, we have seen the characteristics of the laminar premixed flames, such as the laminar flame speed, then the flame thickness, and the structure of the laminar premixed flames. Now, the next topic is the laminar diffusion flames. So, we know that normally the occurrence of fire will be in non-premixed mode. That means fuel vapors or fuel itself is generated in a particular material or some commodity, and the ambient air has oxygen. So, these two will mix, and wherever they mix in the stoichiometric proportions, the combustion will take place. So, let us first see quickly some examples for diffusion flames, and we first go through laminar diffusion flames. That means if the source which gives the fuel vapors is smaller enough, then the resultant flame will be laminar in nature. Three examples have been shown in the figures below. The first one is the candle flame. You know about this. So, candle primarily fueled by wax. So, this is wax, in which there is a wick, and when you ignite the wick, basically a flame forms and sustains over the wick. The wick basically holds the flame, and the flame which is present heats up the wax, melts the wax, evaporates the wax, and the wax vapor is fed to the flame. Oxygen from the ambient is also fed to the flame, so that you get the flame which is intact. This wick is also consumed, this also burns, as the flame consumes the wick as well as the wax, and this flame is quite steady in nature based upon the size of the candle what we have chosen. If you go for bigger sizes, you may see oscillations in the flame and so on. So, this is a small candle which is burning. The second example what is provided here is, you can see there is a porous sphere. See, probably it is made up of some ceramic material which is having some pores, and there is a needle or a small cylindrical pipe which is put in up to the center of the porous sphere. Now, liquid fuel, so in this case it is ethanol, is slowly fed to the center of the sphere, and it comes out radially. The fuel comes out radially and forms a thin film over the porous sphere, and when you ignite it, what happens is the flame establishes over the porous sphere as shown in the figure. In this case, you can see that the flame is fed by the fuel vapors from the surface of the porous sphere, and oxygen enters from the ambient. Now, the porous sphere is spherical in nature, but the flame which is surrounding the sphere is, you can see that there is similarity between this flame and the candle flame, and you can see that the flame stands at a smaller distance in the front stagnation point of the sphere. So, for example, if this is the sphere, this is the front stagnation point and this is the rear stagnation point, as the flow comes from bottom to top. So, in this case, the flow is triggered by natural convection. So, you can see that as the air entrains from this direction, the fresh availability of oxygen and the mixes with the fuel vapor which is coming out of this point, and a flame is established here at a particular distance. And you have to remember that the fuel is fed at the exact same rate as at which it burns. Okay, so how to control this? You try to feed the fuel at a slower rate. If you feed it more than at the rate more than what it is consumed, then what happens is the fuel droplets drips, because it will not have the time for evaporating, so it drips. Okay, if you feed much lesser, then the flame will not be uniformly established over the photosphere. It may oscillate. Some part of the sphere will burn, some part will not burn, because you are underfeeding. So, if you exactly feed the liquid fuel at the same rate at which it burns, you get a flame which is established like this. Again, it is a laminar flame. The elongation of the flame is due to the natural convective flow, and the flame stands at a very small distance from the front stagnation point, and as you move from the front stagnation point to the rear stagnation point, the flame standoff increases. So, this is the diffusion flame which is supplied by a liquid fuel and established over a porous sphere, through which radially uniformly the liquid fuel comes out and forms a film over the surface, and that film evaporates and contributes to the fuel vapor to the flame. The third case is also ethanol, but here you see there is a pool. From the top, if you see, it will be a rectangular slit like this from the top view, and again here also we supply the fuel at a rate at which it is consumed. That means, when you have a pool which is established over this burner and you ignite it, a flame forms like this, the rectangular slit burner, and the fuel is fed at exact same rate at which it burns, so that you have a steady flame of particular height established over the burner. So, here also the liquid fuel surface is basically receives heat from the liquid fuel surface receives heat from the flame and evaporates, and feeds the fuel vapor to the flame. From the ambient, air comes, or oxygen from the ambient comes, and the flame is formed. So, in this case also you can see that there is a heating of a condensed fuel like liquid fuel from the flame, and the flame basically is formed, fed by the fuel vapors from the surface of the liquid and air or oxygen from the ambient. So, in all these three cases, you can see that the fuel vapor and the oxygen mix only at the flame zone. They are not mixed before reaching the flame zone. So, the diffusion flames are called non-premixed flames. Due to the fact that they are mixed only when they reach the flame zone. So, the elongation, the height or extent, what we can say, depends upon how much distance a fuel particle has to travel in order to get the oxygen required for its combustion. So, that is the flame extent, we say flame extent or flame height. So, flame height is the characteristics of one of the characteristics of a non-premixed flame, as opposed to the flame speed what we saw in the premixed flame. Okay, so these are the main characteristics, in which you can see that there is a coupled heat and mass transfer process. In the case of condensed fuels, see, for example, if you have a solid fuel or a liquid fuel, there should be a coupled heat and mass transfer process which should be intact to generate fuel vapors, that is the gas phase vapors, gas phase fuel, which will react or mix with the oxygen from the ambient and form the flame. So, the characteristics of these flames are quite different from the premixed flames. The diffusion, why we say diffusion is because the main transport phenomena or transport process by which the oxygen comes to the flame surface or fuel goes to the flame surface is by diffusion, molecular diffusion. So, the molecular diffusion is quite important or predominant in the case of laminar premixed flames. Okay. So, when you go to turbulent premixed flame, then the molecular diffusion will be enhanced quite a bit. So, we will see those characteristics later. So, now in this scenario, there are 2 or 3 points which we have to understand. First one is the combustion takes place at the location where the fuel and oxidizer mix at flammable proportion close to stoichiometric proportion. That is very important. So, that means the flame edge or flame boundary will be very close to the position or the location where the fuel and oxidizer are mixed at stoichiometric proportion. Okay. So, that means we cannot have a flame which is basically dictated or demonstrated by equivalence ratios here. So, equivalence ratio is close to 1 where the flame boundary is formed. Now, second point is, in the case of condensed fuels like liquid or solid fuels, we need coupled heat and mass transfer process to continuously generate the vapor in whatever be the manner. So, in these cases we have shown steady flames, so that the flame is intact and burn in a particular region around the condensed fuel surfaces. Then the third main point is, the characteristics of these premixed flames are the extent, the flame extent. So, for example, we can say the radial extent and the axial extent of the flame, which is very important. That means, for a particular fuel to travel in the radial direction as well as in the axial direction, the modes of transport is different. For example, in the radial direction, it will be diffusion dominated. In the axial direction, convection will help. In all these 3 cases, we have only shown the natural convection assisting the flame propagation or the flame extent. So, this is very important characteristics of the diffusion flames. Now, let us go into some details of the candle flame. A high quality image is shown in this figure here. We can clearly see the wick here, the wick on which the flame is established, and we can see that the flame has different color zones very near to the base of the flame here, which is very close to the solid surface where a molten wax is also formed. You can see a blue color, non-luminous, we can say non-luminous blue color. That means it is not, we cannot even see it very clearly. There is no luminosity for this flame. Here, fresh oxygen comes and the fuel vapors burn. So, in this particular portion, you can see that in this particular portion, there is no luminosity for the flame. But when you just move up slowly, you can see that the flame actually imparts some color, which is something like a dark brown or orange color. But here the luminosity has increased, but you can see that it is not so bright. Here what happens is soot inception takes place, that is the soot particles form, and over this region I see a very bright color, which is due to soot radiation. The soot particles which form, they agglomerate, becomes bigger particles and they radiate. So, that soot radiation gives high luminosity to the flame, Okay, now we have also shown some typical vectors indicating the radiation heat losses. The red color vectors show that this flame can have some temperature range, say for example 600 to about 1200 degrees centigrade. It can radiate heat to the ambient. The red color vectors show the radiation of the heat from the flame to the ambient. The blue color lines show that there is natural convection which is induced, so that the flame is elongated, and the natural convection also carry the heat from the flame to the environment. And obviously, there should be heat feedback from the flame to the solid surface in order to melt it and vaporize it. That is partly due to radiation and predominantly due to conduction. The green 3 arrows show that predominantly due to conduction. So, the conductive heat transfer and radiative heat transfer assist the heat feedback to the solid wax and melts it, and the heat required for latent heat is also supplied, so that the fuel vapors form and go. So, you can see that the diffusion of the heat, mass, the fuel and air, everything occurs basically. See, for example, in the wick, the fuel vaporizes and it feeds the flame. The yellow arrow shows that the fuel is from the wick goes to the flame surface. From the ambient, oxygen comes and feeds the flame surface. So much activities which are dependent on transport, the heat transport, mass transport, etc. occurs in a non-premixed flame or a diffusion flame. And you can see several color regimes, the yellow, bright radiation, and non-luminous blue color, etc. Several colors also are seen in this. And typical temperatures are given, they may not be very accurate. Typical temperatures are also given. If you see the non-luminous region where it is blue, and the temperatures are not very high, it may be from 600 to 800 degrees. Then if you go to the, when the soot starts incepted, you get some luminosity for the flame. Luminosity is seen. So here the temperature goes up to 1200 degrees centigrade. Then when the soot radiation also is there, the predominant combustion takes place in the gas phase. Temperature builds up to about 1400 to 1500 degrees centigrade. Then towards the tip of the flame, the temperature slightly drops. So these are the characteristics. Unlike the premixed flame, where we saw a conical flame in the Bunsen burner, for example, conical flame surrounded by a non-luminous blue color flame. This conical flame was bright blue in color. Here several colors, several regimes are seen. So when a fresh oxygen mixes with the fuel vapor, a non-luminous blue color is seen. Next to that, soot inception takes place, so that you can see some dark zone. Then the soot radiation gives a very bright zone, etc. So these are the characteristics of the flame just by seeing the flame photograph. Now let us see the structure of a diffusion flame. So let us again take the example of the candle flame. As I told you, a schematic shows very clearly that there is a wick to hold the flame, solid wax, there is some pool of molten wax, and that actually is going to be taken by the capillary effect to the wick, and fuel vapors come from the wick to the flame surface, and oxygen from the ambient goes to the flame surface. This is the flame surface basically. Now, what is structure? As seen previously, when you go in a direction perpendicular to the flame, the variations of temperature and concentration of fuel, oxidizer, products, etc. constitute to the structure of a flame. So, in the case of diffusion flame, let us take a region and go say across like this, from inner some point to ambient. So, I travel in this direction and I try to draw the profiles. So, let us take a profile of temperature first. Temperature in the center is low and it increases to a maximum value at the flame surface here, and then decreases and reaches the ambient side. So, this oxygen side is the ambient side and reaches asymptotically the ambient temperature T infinity. So, this will be the T center, and this is the flame temperature where the flame zone it reaches the maximum value, but it is not exactly going to reach a single point high temperature. It actually goes like this. The real temperature profile will be as shown in this dotted line. It actually increases and reaches the maximum and decreases like this, not a sharp variation like this. So, the temperature varies like this, reaches and goes. So, this shows some variation. This hatch point shows some variation in the temperature due to, see, sometimes the heat feedback will be more to vaporize the molten thing and sometimes it will be less. So, there is some fluctuation in this side, in the fuel side, but in the oxygen side, after reaching the maximum, the temperature decreases and asymptotically reaches the ambient temperature. So, this variation basically is the temperature profile across a flame when you go from a particular point across the flame and go to the ambient side, from the fuel side to ambient side. So, now the region where the flame reaches the maximum value, okay, I can take that region like this and say this is the region where core reaction take place. Do you understand? The reaction take place, the heat actually increases and decreases. So, please see that this variation in temperature is due to conduction from the flame this direction and this direction, and in the reaction zone, since the reaction between the fuel and the oxidizer complete, you will see the maximum temperature is reached there. So, now we can also quantify this. Let us go to the fuel concentration. Fuel concentration, fuel comes here, it is convected and diffused. So, it is called convective diffusion zone, and fuel concentration comes, and due to the variation, diffusion towards the flame, the fuel goes towards the flame by diffusion. Due to the diffusion, the concentration decreases and it is consumed here. The fuel is consumed here. Theoretically, I can say that fuel is consumed exactly at a particular point where the temperature reaches maximum point wise, but it is not possible. That should be, so this, when I say it is closed at a particular point, then the flame has a zero thickness, but in practice the flame will not have zero thickness. So, the fuel actually goes asymptotically to a zero value slightly in the oxidizer side. So, that means some amount of fuel leakage happens and goes to the oxidizer side. So, that means that is again a finite thickness for the flame through which the fuel diffuses, where it is consumed about say 95 to 99%. The when it causes the flame and it is consumed about 95 to 98%, and the small amount of fuel will leak. Again, it will burn as it comes out of the flame, combined with more oxygen and burn. Similarly, the oxygen from the ambient, so this ambient side, oxidizer side, comes, diffuses and again gets consumed in the flame zone. So, it can actually consume at a particular point theoretically, but actually it actually leaks through the flame and gets consumed in the fuel zone. So, that means some small leakage of oxygen, very, very small. Okay. So, we can say about 95% of the oxygen will be consumed in the flame zone, but some few percent will just leak through the flame zone. Fuel can go to the oxidizer side slightly, similarly oxygen can go, and that means the reactive zone or the zone where major reactions take place, heat release reactions take place, will have a thickness del, as we saw in the premixed flame. So, there is some thickness for the flame. it cannot be exactly 0. But please understand that even if I say that the del will tend to 0, it is fine for us, because there is no big role for the chemical kinetics to control this. It is basically the transport of the fuel vapor to the flame zone from the fuel side, and from the oxidizer side, the transport of oxygen to the flame zone. So, this transport process controls. See, for example, let us say that the fuel comes out at a faster rate. Then what happens? The flame radius will be higher, because the fuel will push the flame zone to the oxidizer side. Or on the other hand, if there is a convection happening and the oxidizer comes to the flame zone at a faster rate, then the flame radius will reduce. Flame height also will reduce. That means the flame extent, the radius or the height, depends upon the rate at which the fuel and oxidizer are transported towards the flame zone. So, that is very important thing here. So, transport processes control the flame extents. So, that is the important thing. On the other hand, for a premixed flame, we have seen that the kinetics play a very important role. Here, the kinetics can be even neglected, or if you want to really use the single step kinetics. So, now let us move on to gas flames. Okay. So, I have shown a figure at the top to just indicate that how a photograph of a premixed flame looks like. So, we can identify that, just to recall, there is a inner cone, bright blue color, and the outer zone, I can say, diffusion flame. So, this typically is a stoichiometric premixed flame of methane and air. Now, let us say that I have a jet of a gaseous fuel, same burner, I do not premix, only supply the gas fuel, and this gas fuel, let it be LPG, and when I supply this through this port, etc., I now get a flame which exactly has the same color features as the candle flame, like it has a non-luminous zone, a dark zone, and a bright zone. Well, all exactly three things what we saw in a high definition photograph here: a non-luminous zone, a darker zone, and a bright radiative zone. The same thing you can see in these flames, and the photographs show the variation of the fuel flow rate and the typical flame height resultant from these flow rates. See, when I increase the flow rate from 2.7 liters per hour to about double of that, 5.6 liters per hour, you can see there is a increase in the axial flame extent. The radial flame extent does not change much, but the axial flame extent increases. So, why it is? Because you can see that the fuel which is coming out has to obtain the oxygen only from the ambient, unlike the premixed flame case where the oxygen is premixed with the fuel, so that it just burns coming out of the burner port. Now, this gaseous fuel flames, just only fuel comes out of the cylindrical pipe or an orifice, etc., is called jet diffusion flame. That means the fuel jet comes out, it entrains oxygen from the ambient. Wherever the fuel gas and the oxygen mix with stoichiometric proportion, a flame is formed. So that the surface of this flame, etc., will be the locations where the fuel and oxidizer have mixed at stoichiometric proportion. Okay. Then the color differences between the premixed and the diffusion flames are quite clear. The premixed flame is normally a blue flame which has some luminosity, but not the luminosity what the diffusion flame can impart. That means the diffusion flame can, see, if you have a dark room and have a candle flame, it will lit the room, like the room, we can see the objects in the room because of the luminosity of the flame. But if you have a premixed flame in a dark room, it will not be able to show the materials there. So, it is not so luminous. So, the luminosity is the main difference between the diffusion flame and the premixed flame. Second one is, there are multicolor zones in a diffusion flame. Here there is only one inner brighter cone and outer dull blue color zone. So, two flame zone is there. Third one is the flame extent is the characteristics. Here the rate at which the premixed reactants are consumed by the flame as it goes normal to the flame is the flame speed. That is the characteristic of a premixed flame. But in the case of a non-premixed flame or diffusion flame, you can see that the flame extent, as the fuel flow rate increases, obviously we are in the laminar regime now, we can see that the flame, the axial extent of the flame increases, and this increase is due to the fuel particle has to get the oxygen from the ambient and it has to travel a certain distance to get the required oxygen to burn. Then the surface of this flame is nothing but the location where the fuel which is coming in from this side and oxygen which is coming from the ambient side mix at stoichiometric proportion, near stoichiometric proportion. So, the bright yellow color is due to soot oxidation here, and the orange color etc. is due to soot consumption. So, there are lot of phenomena which is going on in the non-premixed flame.